Different things are intuitive to different people, and when you're explaining something that you think is pretty intuitive, that's intuitive to you, you have a tendency to gloss over details, to assume knowledge in the other person, and fairly often to not even realize you're doing it. And this becomes a problem when you're trying to educate yourself and when you're trying to educate others. This is the problem I faced when I was trying to get into operational amplifiers, op-amps. Pretty much every reference I found starts the explanation with diff-amp. Differential amplifiers. It's sort of step one on the way to building an op-amp. And pretty much universally, they all said something similar to, the differential amplifier uses a positive and negative power supply, a dual power supply, to make sure the transistor always has enough power. And this is where my blank stare comes in. Because when somebody says they don't have enough power, it seems to me that you want more voltage, or you want more wattage, more power capacity, or something. Not a negative power supply. It was just nonsensical. And some of you are probably looking at this video like I'm an idiot now, but don't worry about that. Like I said, it truly is not intuitive to everyone. Now that I understand it, it's actually pretty easy and clear, and I feel dumb for not having gotten it. But it still isn't intuitive. It's easy to understand now that I understand it, but it's not intuitive. So I'm going to explain this to you in a much simpler way and not gloss over details, hopefully, so that if it's not intuitive to you, you don't have to go through the same trouble I did. Now, I'm not going to explain differential amplifiers right now. That's a topic for a video all its own. But essentially, if you recall the common emitter amplifier, you have an input signal, and then you have a transistor, and it goes through the transistor, and then you have an output signal. In a differential amplifier, you actually have two of those. It's pretty much the same circuit, minus the bias. It's mirrored. It's the collector resistor, transistor, and emitter resistor, except there's two of them. And you have two input signals, and your output, see, normally you'd take the output from above the transistor. Well, you take both outputs, the positive and negative output essentially, from the tops of each transistor. Sort of like the H-bridge. Remember the H-bridge had two inputs and two outputs? The same way. You have two inputs and it amplifies the difference between the inputs. Not a signal relative to ground, but two signals relative to each other. And then the output is again the difference there. But like I said, that's for another time. Right now, I'm going to explain to you about the dual power supply thing. So for a standard common emitter amplifier, we have our input signal, and that is relative to a common reference voltage for the circuit. Anytime we're using signals, we need a reference voltage that the whole circuit uses. So one end of this is to the relative reference voltage, and the other end comes out, and you have your signal resistor, you have your capacitor to block off the bias from getting in, then you have the power supply for the amplifier itself. You have your two bias resistors, so the power goes in to the bias resistor, the capacitor, and this come through, and then of course we have our reference voltages again. We have our transistor with the collector and emitter resistors, and the same power feeds this one, goes through the transistor and out to the reference voltage. The signal connects there, and this is the signal output. So the bias sets the base, essentially the voltage of the base at a midpoint. So the bias interacts with the emitter resistor. You have a certain voltage. So if you have 0.7 across base to emitter junction, you might have 1 volt here for a total of 1.7. So the base would be at 1.7 and the emitter would be at 1 volt. And then that's when the signal is 0 or not present. And then the signal goes positive, negative, and that 1 volt goes to above 1 volt, below 1 volt, and varies that way. And then you set up your currents and whatever to get the gain you want. But the point is, the bias with the emitter resistor moves the base to emitter voltage, the base voltage, and the emitter voltage up so that the transistor is always on and it's in a range, so the base to emitter junction never turns off. Yes, I just realized I drew that line wrong, but you got the point. That goes there. But this is not really a great way to do it for a differential amplifier. It's too complicated, there's too much extra crap going on. So instead of biasing the signal, we just want to have this emitter resistor have a voltage all its own. What if we didn't need any of this? What if we didn't need to use this bias trickery to move this up, right? Because normally with a signal at 0, the base and emitter are going to be at 0, and then you move the signal up to 0.7, and now the base is 0.7 and the emitter is 0. And if you move it up to 1.7, then the base is 1.7, the emitter is 1. And if it's negative, of course, it's still off until you break your transistor, which is why we need this wiggle room. But what if we could just put the transistor higher? If we think of this as a distance, what if we could just give it space without anything? Just plug the signal directly into the base and let the transistor move up and down within this margin without having to have this extra circuitry to do it. That is how the negative power supply works. Basically, you have the positive power supply doing all of this, and the negative power supply biases this, not biases, but applies a voltage to this resistor so that when the signal is 0, the emitter is at the voltage you give this resistor directly. I'll show you in a second. But let me just remind you of the video I did where I had 2 power supplies and you can interconnect them as long as you only interconnect them at one point. That's how this works. You have 2, in fact, you have 3 power supplies, 3 EMF sources, voltage sources. The signal, the positive power supply, and the negative power supply. In this one, you have 2. The signal and this power supply are separate. So let me show you how to bias a transistor with 2 power supplies and no voltage bias circuit. So just like before, we have our transistor. We have a collector resistor, and we have an emitter resistor. We have a power supply. This power supply is over here feeding this transistor. So the positive of the power supply through the collector, through the transistor, through the emitter, and this end of this power supply is connected to the common reference voltage, the circuit ground. The emitter is not. Hold that thought. So now we have our signal. One end of the signal is connected to the reference voltage. We have our signal resistor, just to make sure that it's a nice high impedance thing, which goes straight into the base. Nothing else. No capacitor, no voltage divider, no nothing. Right into the base. This is our positive power supply. This is our signal. So I need another power supply. And this is going to be the negative power supply. Now, why is it called a negative power supply? Well, it's because of the way it connects to the reference voltage. I'm going to connect the end of the emitter resistor to the negative of this power supply, and the positive of the power supply is going to the system ground, the circuit ground, the reference voltage. So one side of the signal is at reference, the negative of the positive power supply and the positive of the negative power supply are both at reference as well. How does this work? Remember the simple analogy of going downhill. You've got positive charge one side, negative charge another. You've got an electromotive force from the difference the electric field propagates. But essentially, they call voltage a potential difference. Where you say you have a high voltage and where you say you have a low voltage, electricity will try to flow. Going from high to low, by conventional current, the electrons go the other way. Don't worry about it. So think about it being on a hillside. You have a ball on the side of a hill, and you're holding it there, but gravity is trying to pull it down. When you let it go, you've connected your circuit, and it's going to roll down the hill until it reaches the low point, the bottom of the hill, or a ledge that you've put there. It goes from a potential energy point to a potential energy point, and that's the electricity flowing. It goes down an energy level. If you have 2 power supplies, it's like you have 2 ledges, right? And you're saying that the middle ledge is 0. So you've got positive up here, and you've got negative down here. Positive power supply, negative power supply. So it's the same thing. It's just you're at the top of the hill and you roll down to the bottom of the hill. But the middle point is where you say, okay, everything is referenced to this. This is 0. So that's why lower than 0 is negative. It's just a perspective thing. The electricity, the electric field doesn't care about any of this. All it knows is high energy state, low energy state. That's pretty much all of physics, is you've got energy states and it goes from the higher one to the lower one, and welcome to entropy. So imagine if your signal is at 0. It's at the reference voltage. So 0 here, so no voltage. So the reference voltage is here at the base. Base is at 0. Well, look at what base is connected to. The reference voltage is connected to the positive end here. The negative end is at a lower voltage than the positive end. So you've got the reference voltage here, and you've got something lower than the reference voltage here. So electricity is going to try to flow. And look at where you have your circuit. Positive, right? Because conventional current goes out the positive end. So you see out the positive end, to the reference voltage, which is connected over here, through the signal, which is at 0, through the resistor, through the base to emitter, and the emitter resistor back to the negative end of the power supply. So we have a loop from the positive end of a power supply through circuit elements in the proper direction to the negative end of a power supply. That's a normal circuit, isn't it? That's a normal circuit. How about this one? We start at the positive end again, so we go out the positive end of the power supply into the reference voltage, connects up here as well, goes into the negative end of this power supply, and pushes this one, so they're in series. All right, two power supplies in series, they're adding their voltages. So it pushes out the positive end here through the collector to emitter in the correct direction, around here to the negative of the power supply. If we don't worry about this weird, unintuitive, at least to me, setup, then we can look at it and see how it flows just like normal. Power supply positive all the way around back to power supply negative. It works. Because you look here, you say, okay, well, if you look at the positive end here and it goes through here, but then it's connected to the negative end, but then it continues. They're in series. These two are in series. So when this signal is at the reference voltage, the base is at the reference voltage, the emitter, this emitter resistor, is connected to the lowest part of the circuit, which is this much voltage below the reference voltage. If this is 5 volts, this might be 0 volts, this might be negative 5 volts. So this would be 0, this would be negative 5. And so Ohm's law and currents and all that other stuff determines what the voltage drops on the resistors are, but the point is, there's always going to be a voltage drop here, as long as the signal doesn't go too crazy. If you have a 5 volt power supply here and your signal goes to negative 6 volts, then it's all going to stop again. But the same thing would happen in the common emitter amplifier. Your emitter resistor was configured for 1 volt at quiescence, so you add 1.7 volts, so you bias it to 1.7 volts, and you've got 1 volt of wiggle room. 0.5 down, 0.5 up. Actually, yeah, 1 volt down and then more up, because it's however much your supply voltage is. But you can go up to a volt down before you risk turning off the transistor. So you can go this power supply down on the signal before you risk turning off the transistor. Well, this power supply minus, so if this was 5 volts, it'd be 4.3 volts. So your signal could go down to minus 4.3 before turning off the transistor, because you would have your 5 volts here, your 0.7 volts, and that's 4.3. So if you counteract it, it comes back down. But that's the beauty of it. It looks weird. It looks weird. It looks alien that you're connecting positive to a reference voltage, but it works. So let me show you with a breadboard. So I have 2 power supplies and my oscilloscope. And on my breadboard, I have some 10,000 ohm resistors, 10k ohms, a regular NPN transistor, and an LED, so that you can see what's going on. Both of my power supplies are going to be set for 5 volts. And I'll go ahead and turn the current limit up to 10 milliamps to make sure they're trying to supply that voltage. And then I'm going to use the wave generator on my oscilloscope. It's just going to put out a DC signal. So this is just essentially a third voltage source that I can turn up and down easily with a knob. So if I come over here, this will be the positive power supply, this will be the negative, and this will be the signal. So I'm going to first connect the negative of the signal to this trace down here, which is going to be my system ground, essentially. My circuit ground, my common reference voltage. Furthermore, I'm going to connect the positive of the signal through a 10k resistor, that's the signal resistor. The output of that resistor is going to go into the base of the transistor. The signal is currently at 0 volts. I'm going to take the positive of the positive power supply through a 10k resistor to act as the collector resistor, out of that resistor through an LED just so we can see what's going on. This is essentially the output and the load. This is the LED is in series of where you would take the output. So we'll connect that to the collector, and I'll connect the emitter. Actually, I'll leave the emitter for alone for a moment. So I'll connect the negative of the positive power supply into my little shared ground spot. And now for the negative power supply. The positive of the second power supply is going into the ground location, and the negative is going to connect to the emitter resistor, which the emitter resistor I have to connect to the emitter, obviously. And once I do this, the LED turns on. Hopefully you can see that. Is it bright enough? Should be. So the signal is 0. The signal is 0. So essentially there is 0 voltage between the positive and negative of the signal. The negative is connected to the shared system ground. The positive is at the negative's level, so it's 0. And yet the transistor is on. What if I disconnect the signal? The LED turns off, because it still has to have the current through the base to emitter. It still has to have that circuit going on. It's not like a JFET that's default on and then you bias it to turn it off. Without a base connection, it doesn't matter how much you bias, it doesn't matter how much voltage you put in it, it's not going to transmit. It might explode, but it won't transmit. So I do have to have this 0 signal connected to turn the LED on. Let me look at the voltages. So if I connect the negative of my multimeter to the shared ground, if I connect it to the positive of the signal, it's 0. The negative of the signal, it's 0. The positive of the positive power supply is reading 5 volts. The negative is reading 0. The positive of the negative power supply is reading 0. And the negative is reading negative 5 volts. And if I were to measure at the bottom of the emitter resistor, I get minus 5 volts. At the top of the emitter resistor, I get minus 1 volt. So the emitter is at minus 1 volt. The collector is at minus 1 volt. This transistor is in saturation. But what about the base? If I measure at the base, I get minus 0.44 volts. So if we go minus 1 to minus 0.4, let's call it minus 0.5, we're getting about 0.5 to 0.6 volts, which is within a reasonable window for the voltage drop of the base to emitter junction. So it's negative by a little bit because of the voltage drop of this resistor over here. If I measure the signal resistor, on the right is minus 0.45, on the left is straight 0. So there's a small voltage drop on the signal resistor. So at 0 signal, the base is slightly below 0, and then the further voltage base to emitter from that, and then the emitter resistor is taking whatever it wants to take based on Ohm's law. So if I were to turn this signal down, let's watch the LED. Let me put it in shadow, might be a little easier to see. So I'm going to just turn this signal negative. Right now it's negative 1 millivolt. Let me give it another kick. Negative 160 millivolts. Nothing's happening. So let me keep turning it down. I'm just going to watch the LED until the LED goes out. And oh, it's starting to dim. Do you see? Now it's changing in intensity. And if I turn it to about there, it looks like it's completely off. And what do I have? Minus 4.5 volts. So recall, we were getting minus 1 volt to minus 0.45. So that's about 0.55 volts for the base to emitter. Well, we're about 0.5 away from negative 5. So interesting that, isn't it? If I measure the voltage, once again, at the output of the emitter resistor, we're at the minus 5. If I measure the emitter is at almost minus 5. We've driven down the emitter. The base, see, there's the emitter, minus 4.94, and the base is at minus 4.46. So it pretty much doesn't have quite enough voltage to be forward biased. But we had to go all the way down there and push the base down towards the negative end. So a normal signal that's not got that much amplitude is going to be passed just fine. The transistor is going to be in its always on state, its active state, just like with the common emitter resistor and the bias, except we're using a negative power supply instead of a voltage divider. And the signal is much more stable because of it. The circuit is much more stable and much more simple at the cost of 2 power supplies. So there's a trade-off there. But this is what I wanted to illustrate, is this is what it means to use 2 power supplies. You are tricking the system. We think of the ground, the reference voltage, the 0, we see 0, that's the lowest point. That's the thing that's not intuitive. You get into that rut of thinking that you have your power supply and you go down to 0. And that's how your circuit works. But 0 is whatever we decide it is. It's a reference voltage. It can be anything. 0 could be the positive. And you could never have a positive voltage in your whole circuit. You could go from 0 to negative 5 with the 5-volt power supply. It doesn't matter. What matters is your positive and negative is essentially which way is down. So 5 to 0 is down. 0 to minus 5 is down, minus 5 to 0 is up, 0 to 5 is up. So the voltage difference from the positive power supply to the reference voltage is positive 5. The voltage difference from the reference voltage to the negative of the negative power supply is positive 5. You've gone down 5. So just hammer into your brain, your reference point is just anywhere you say, that's the reference point. And then you've got up from there and down from there is positive and negative. And that's it. So while you ponder this deep truth, I'll be seeing you.